Today I present to you Lecture 4 of the FIR filter series. Today we are going to discuss choosing window functions. Last lecture we looked at choosing impulse responses of our filter. Last lecture. Now today we will look at the most basic type of window function known as the rectangular window. The window function is step 3 in the procedure of building an FIR filter. That's why we need a window function. Let's get a bigger eraser first. Rub everything out. So why do we need windows? Why do we need a window? So if you remember, the impulse response of a low-pass filter, an ideal low-pass filter, looks like this. Symmetric. If you remember, it also goes to infinity, plus infinity to minus infinity. This will go on forever. That will go on forever. Now, if you look at the definition of an FIR filter, let's change our color. FIR. This is finite. F stands for finite. We cannot let our impulse response go on forever. It has to stop somewhere. Now, to make it stop somewhere, we apply a window function. A window could be like that. And this window, call it window, will restrict this orange impulse response to here and here. And all of this is gone. This has now made our impulse response finite in nature. So if I rub everything off and show that a bit better. So you have your sync wave that's going on forever. You then apply a window function. So window. And the result, purple is a nice color, is now your finite sync function or your finite impulse response. And this is all you get, a finite impulse response. And that is all a window function does. It constricts the time for the impulse response. It prevents it going from infinity and minus infinity. Keeps it to a certain point. Many types of window functions, so let's look at that. Window functions. There is a long list of them. You have the most basic, the rectangular window. You have the Hanning window. You have the Hamming window. Notice that's an M. Hanning window. You have the Kaiser window. And this long list goes on forever. There is a large number of windows that engineers and mathematicians have made. However, we are going to today look at the most basic type of window, which is a rectangular window. Now, the rectangular window has the least performance. This basically means that if you use a rectangular window, you're going to get the worst possible FIR filter you can think of. It's not going to have the best frequency response. It's just a worse performing window. Things like the Hanning window, the Hamming window, they have way better performance, and that's why these windows tend to be used in the real world. Kaiser window allows for more advanced parameters to be applied to your impulse response. Now, it's important to note that rectangular windows are just simple to apply and simple to understand, so that's why we're going to learn about it first. However, you will never use a rectangular window in the real world. Its performance is just too bad. It's just not good enough for use in the real world. However, in later lectures, we will look at these window functions, and we'll see why they're a lot better. Exactly is the rectangular function. Rectangular window function. So if you have your sync wave or your low pass impulse response, it's a low pass impulse response. The window function or the rectangular window function simply multiplies everything inside by 1. So multiplies by 1. And everything outside the rectangle function is multiplied by 0. Multiply by 0. Multiply by 0. This means that everything outside the rectangle is removed. Everything outside the rectangle is removed. And the rectangle only keeps everything inside it. Now, there are other functions. Let's just remove this. Now, we did say there was the Hanning, the Hamming, there was also the Kaiser, and they have a slight different shape. And instead of a sharp rectangle like this, they will typically have something like this. Can you see how it's not as sharp as the rectangle? Not as sharp as the rectangle. So, and they will have different performance benefits. But for this orange rectangle we have here, everything inside this rectangle is multiplied by 1, which means that it's there, it's kept, and everything else multiplied by 0, and they're gone. And that's simply all a rectangular window is. Remember our impulse response of a low-pass filter, ideal low-pass filter. The rectangular window is just a simple rectangle. That's our rectangular window. Now, a key point to understand is the only parameter you can change with the rectangular window is how far it goes for, how long the filter is, how long the window is, sorry. Now, the longer your window, so let's write that, longer window equals a better filtering performance. This is an important thing to stress. So if you have a small filter window, this is going to be a worse performance. And if you have a long window, all the way down here, you will have a better filter performance, So how do you actually determine what this length is? What determines how long the filter window is? Well, this is based on the filter order. So let's rub some stuff out. So a filter order, larger filter order equals a larger or longer window length. Now, when we remember from previous lectures, a low order filter, so let's draw this, will have a larger transition band, and this is our transition band, and it rolls off slower. Now, that is a low order filter, low order. However, a higher order filter will have a very sharp transition band, a very small transition band, and very sharp filter response, high order. And so now this higher order filter would apply to this longer window length, and this lower order filter would apply to this shorter window length. So therefore, a higher filter order means a longer window length. A longer window length means that we capture more of the impulse response in time. This makes a better filter, a filter closer to the ideal filter. Now, be wary that a higher filter order means you require more computational performance. However, it does mean a better filter performance in the end. Now, it's important to stress that this window is always symmetric. Window is symmetric. That means it's equal on the negative side and equal on the positive side, though it may not look like in the graph, but the window is always symmetric. So let's rub all of this out and redraw the sink or that low pass filter response. So remember that it's our sink wave or our low pass impulse response. And we apply our window. Now the full window length is equal to something called, well, you guessed it, the filter length. But how does a filter length correspond to the filter order? Well, filter length equals filter order plus 1. Now, another thing that's important to stress is that you should typically have an odd filter length. An odd filter length is always more advantageous than an even filter length. And to have an odd filter length, it is ideal to have an even filter order because even number plus 1 makes an odd number. Now, why is odd and even important? Well, we'll discuss that a little later in the video, but just keep that in mind. Odd filter length is better than an even filter length. So by having a longer filter length, you can capture more of the sink wave, but remember, it's also symmetric, so it must go on both sides. So that is, a longer window will have that, and these parts are all the same length. It is a symmetric window all the time. Any window you use is always symmetric. Now remember, we are in the time domain, so if I draw our impulse response that is windowed, this is into the time domain, and this is not acceptable for a computer. A computer will not accept time domain. It will only accept it in samples. So to do that, we just sample this wave. So that is n equals 0, n equals 1, 2, 3, 4, and then it also goes the other way around too. So -1, -2, -3. And that is how a computer gets its FIR filter coefficients. So filter coefficients are simply just these samples here. You've sampled this impulse response that is windowed, and now you have these red dots here. And these values of the red dots are the filter coefficients. Computer stores all these filter coefficients in an array. Stores in an array. So if you've ever used an array in, say, C++, C, Python, An array is just like a series of numbers. That's basically it. A simple data structure used in computers. So filter coefficients will be an array of, so that's n0, n1, n2, n3, n4, where all these apply to all these coefficient datas. Now it's important to stress that you don't get a -1, like you won't have n minus 1, like a -1 element. So these are called elements in an array. You don't get a negative element, that doesn't exist. So n equals 0 has to be all the way here. Like this would be n equals 0, and this would be n equals filter length. So let's just draw that so that looks a bit more clearer. A pen. So this is our windowed impulse response. Windowed impulse response. And when we sample this and store this into our array, we use n equals 0 here, n equals 1, all the way here to n equals filter length. So the size of our array is equal to the filter coefficient array, has a length, so it's a size of filter length. So that's how long it is. So the larger your filter length, the larger your filter coefficients array is. So another point here is that the sample in the middle, if we have, like bang on the center, if you have an odd array here or an odd number of filter coefficients or an odd filter length. So if you have an odd filter length, then we get t equals 0. So this middle point here, and important because it allows for a linear phase. So remember when I said that a filter length that is odd, so filter length odd is good because it allows us to sample bang on this point here. And that gives us a linear phase. And that is also a symmetric filter too. That makes it symmetric, so it gives us a linear phase. Now, if you have an odd filter length, if you have an even filter length, you do not get this. You do not get that line. This sample here only happens if you have a filter length that is odd. So only if filter length is odd. So that's why we tend to use a filter length that is odd. Now, to have a filter length that is odd, you need an even number of filter order because filter length equals filter order plus 1. So for this to be odd, this has to be even. So yeah, that's that. So remember, filter coefficients is an array that a computer stores, and that is full of all these coefficients here. It stores all these coefficients from here, here. Remember, it's symmetric, so it goes both ways. So all these blue lines you see over here, they're all the filter coefficients. These are all our filter and we store it into this array called the filter coefficients array. A longer filter length means that the filter coefficients array is longer, which means you now require more computational power because that is just more mathematics required to do. And at the same time, more filter coefficients means you capture more of the impulse response, which in turn means a better filtering performance. End result, oh, that's a pen we need. The end result of all our previous lectures is just an array of filter coefficients. Where you remember that if you have an impulse response, the filter coefficients are just these that are sampled. These are sampled, and that gets us our array of filter coefficients. Now I've called these n1, n2, etc. However, most textbooks will call it, so say if you have an array, we'll call it a1, a2, a3, all the way to an, where n is the filter length. So the last element is the element filter length. This means a larger filter length means a longer array. So larger filter length equals longer array. And that's it. That is your FIR filter. Your FIR filter, let's change color, is just an array of filter coefficients. Once you have all these values, that's it. Your FIR filter is now complete. But how do you actually use those values? Now you convolve this array with your input signal. Let's look at that. So say you have your filter coefficients, your build your FIR filter coefficients, which is an array, remember, A0, A1. I'll call these A's instead of N's, A3, all the way to AN. Now, AN minus 1, because a computer's array starts at element 0, so we just say AN minus 1. And we just convolve this with the input signal, with an input signal. So this input signal could be an array of, say, your sensor value, so we could call B1, B0, because it starts at 0, B1, B2, all the way to Bn minus 1. This input signal could be your sensor value or new sensor input audio, anything. Anything that a computer has just come up with, it has sampled, and you want to filter. So by convolving your FIR filter coefficients with the input signal, you have now got a filtered output. And that's simply how an FIR filter operates. You find your coefficients here, which we've discussed over the last few lectures, of finding your impulse response, then windowing it, and then sampling it to get your FIR filter coefficients. And then we convolve this with an input signal, and the output is a filtered output. Now, next lecture, we will look at how to do this convolution operation and its importance. And that will finish the basics of FIR filters. And then after that, we'll look at the more advanced stuff of FIR filters. Thank you. Please like and subscribe, and please comment about how you found the video or any questions, and I'll be happy to answer them. Thank you. See you next time.